All right, so we needed to come back to the second part of talking about the Step 1 tutorial program of deal.II as part of my Math 676 class. So in the first part, I've shown you how to create the very first mesh, something that was quite trivial. We just created a single cell for a square, and we refined it 4 times, and we output it. What I would like to show you this time is, for a more complicated geometry, how you have to think about a triangulation as a collection of cells. So the way you do these sort of things is, if you go back to step 1. So step 1, as I said, we always read it from the bottom. So there was, in main, we call the first grid function. We talked about this last time. This time we talk about the second grid function here. So second grid is a little bit longer, but it still fits on one page. It's almost. So what we do in this particular case is that we create a triangulation object, just like the last time. And again, we create a 2-dimensional triangulation. And what I would like to do is create a mesh that describes an annulus. And let me show you the end result that I want to achieve. And I think that gives you an idea of, let's say, why the code does what it does. So I would like to create a mesh that looks like this. So it's going to start out essentially as an annulus that consists of 10 cells. So if you later you will see this in the code. So it starts out with 1 cell here for this whole thing, and then another cell here, and another cell here, and then we're going to refine it a number of times adaptively. So we're going to take this one big cell that used to sit here, this quadrilateral, and we're going to split this into 4. And then for the 2 small ones down here, we split them into 4 again, and here. And so every time we do this adaptive refinement, we refine all of the cells that sit at the inner ring of this annulus. That's sort of the goal that we have. And so, keeping this in mind, let me show you how we do this. So we start out by creating a triangulation, okay, which again you could think of as a collection of cells that in the beginning is empty. And then we would like to call a function that is called grid generator hypershell that takes the following set of arguments. So if I click on hypershell, I come out at this documentation for this function here. Okay, so the argument list is a triangulation, a point in dim dimensional space. So for now we always have something in angle brackets that's 2, so that would be a point in 2-dimensional space. Then the hypershell in 2D, of course, is just an annulus. So we need to pass a third argument, the inner radius, as the fourth argument, the outer radius, and then there's 2 default arguments that you can read up in the documentation of this function if you want to. So what we're going to do here is, as the first argument, we pass the triangulation, right? Then the second argument was the location of the center of our domain. So we need to define a point in 2 dimensions that denotes where the center of this annulus will be. So we create an object called center of type const point 2 that has coordinates 1, 0. So x equals 1, y equals 0. That will be the center, and then we give as the inner radius 0.5 and this is the outer radius 1. So these are the arguments that we pass here. And then the number of cells, that's the number of quadrilaterals on the perimeter, that will be 10. Then there are 2 lines that I'll come back later to, this boundary description here. So let me ignore this for a moment, and I'll show you in a second what the effect is if I didn't have these 2 lines there. So let me forget about this. But then what we'll do is we're going to do 5 steps of always refining towards the inner edge. And now comes the point where I talk about a mesh as a collection of cells. So after we call hypershell here, in this function up here, our collection of cells, this triangulation, will have exactly 10 cells in it, right? So it's going, you can think of this as a list of 10 cells. And so what I'm going to do is in each one of these steps, I'm going to loop from the very first up to the very last one of these cells. So if you think about how you learn in when you program C++, how you typically do this is you get yourself an iterator to the first element, you get yourself an iterator to the one past the end, and then you have a loop over all of the elements in between. So in deal.II, this typically looks like this. So you write the data type, that is triangulation 2, : active cell iterator. And I'll explain in a second what that actually means, but essentially you can think of this as a pointer to individual cells. And I'm going to define two objects of this type. The first one is called cell, and I initialize this with begin active. That is the first cell in this collection of cells that make up the triangulation. And then I have an iterator end C, that is the one at the end. Okay, actually it is the one past the end, so it's an invalid iterator. When you hit this one, then you have traversed all of the ones in between. And so I'm going to loop over all of the cells in this for loop here. So when you, as you remember, the goal was that we refine the mesh always towards the inner edge. So what we have to do is we have to find out for each one of these cells, or let's say for the cell that we're currently on, right? So we have this loop over all of the cells. When we're in this loop, we ask the question, is this a cell that's sitting at the inner edge of our annulus? And the way we're going to ask this question is one of the four vertices of this cell, is one of these four vertices exactly 0.5 away from the center of our domain? Okay. So what I'm going to do is, so I'm sitting on a particular cell given by this iterator cell. Okay. And then I'm going to loop over all of the vertices of this cell, and we know that in 2D the vertices of a quadrilateral, there are exactly 4. In 3D there are of course exactly 8. In practice we're oftentimes a little bit too, let's say, too lazy to remember exactly how many these are, and we use a class that is called geometry info, in this case 2 because we're in 2D, that has a variable that is called vertices per cell. Of course, geometry info 2, vertices per cell, is equal to 4. Geometry info 3, vertices per cell, is equal to 8. The point that I want to make when we write it like this is that we use symbolic names because it avoids us to make mistakes. So, for example, if I asked you the question, how many sides does a cube have, you might be tempted to say 8. Well, that's not quite right. There's 6 faces for a cube, even though there are 8 vertices of a cube. Now, these sort of mistakes are easy to make, and it's a lot easier if you use these symbolic names because you never make these mistakes. The code also becomes a lot more readable because you just don't write 4 or 8, but you actually give it a symbolic name, vertices per cell. Everybody knows what that is. You will find a much more important use of this at a later time when we try to write programs in such a way that they're independent of the space dimension, so that you can run the same program in 2D and in 3D. Because in that case, if you wrote 4, that's correct for 2D, but not in 3D anymore. Whereas if you wrote 8, it's correct in 3D, but not in 2D. And so if you wanted to write programs that are independent of the space dimension, you would have to have conditionals in all of these places where you ask for the dimension and so on and so forth. That is a prescription for errors. So in cases like this, you will always use the geometry info and then, well, some placeholder argument instead of the 2 or the 3, and vertices per cell. And the compiler will later replace the placeholder by either 2 or by 3, depending on whether you run your program in 2D or in 3D. So you will really learn to appreciate the information provided by geometry info. Okay, so to come back to the question, we wanted to loop over all of the vertices of a cell and find out whether one of the vertices is at the inner edge of this domain. Okay, so what we're going to do is, so we're sitting on a cell given by this iterator cell. V is the number of the vertex between 0 and 4, in this case in 2D. And so we're going to ask, what is the distance of this particular vertex, of this particular cell, from the center? And so here's one way how you can query information about cells. So I told you that cell is an iterator, which you can think of as a pointer to a particular cell. So if you write cell arrow, that gives you that dereferences the pointer to the cell, and the cell has a function that is called vertex. That you can give it the number of the vertex that you want. So let's say v, for example, is 2. Then cell vertex 2 would give you the coordinates of the second vertex of a cell. And then I can ask the center. Center was an object of type point. Okay, so if you can ask the center, what is the distance between the center and this particular vertex? That's of course just a number, particularly it's a positive number or a non-negative number. I'm going to store this in this double variable that I call distance from center. And now I argued that if a vertex has a distance of 0.5 from the center of the domain, then it must be on the inner ring of this annulus. It turns out that in computer programming it's a tremendously bad idea to compare two floating point numbers for equality, because things are only equal up to round off. It never happens that you take the difference between 2 points and it comes out to be exactly 0.5. What will happen in practice is that it will come out to 0.500000001 or 0.4999998, something of that kind, where the difference is very small but not 0. And so if I write if distance from center equals inner radius, for example, you will find that that will never be true, even though the point actually does lie on the inner perimeter, on the inner ring of or on the inner circle of this annulus. So in reality, the way you have to write these sort of questions like, is the distance of this vertex from the center equals to 0.5, that is equals to inner radius, the way you have to phrase this is always is the difference between these two floating point numbers, the absolute value of this, is this less than some sort of tolerance? So in this case, I'm going to ask if the distance from center is greater than 0.5 minus 10 to the minus 10 and less than 0.5 plus 10 to the minus 10. That's what so if this condition is true, then I will say that the distance is in fact 0.5. And so if this is true, so if I have just found a vertex for which if I have found a cell for which one of the vertices is equals to 0.5 away, or a distance of 0.5 away from the center of the domain, then what I'm going to do is I'm going to say cell arrow set refine flag. So that means I'm going to mark the cell for refinement. If I have found one vertex of a cell that is on the inner circle, then I don't need to look at the other vertices anymore. So I can say break, and that jumps out of the innermost for loop, namely this one here, and just moves on to the next cell. And that's really all I want. So I'm going to go through all of the cells. For each cell, I'm looping through all of the 4 vertices, or until I have found one that actually sits on the inner circle. And so at the end of this entire loop here, I will have marked all of the cells that sit on the inner perimeter of this circle. So right now, all I have done is I marked them for refinement. That's what this set refine flag does. It doesn't actually refine these cells yet. It only marks them for refinement. And so the next step that I have to do is I have to call a function that's called triangulation, execute coarsening, and refinement. And you see that again, I could click on this here if I wanted to see the documentation for it. So what execute coarsening and refinement does is it takes all of the cells that are marked for refinement and replaces them by the 4 child cells. It also takes all of the cells that are marked for coarsening And if all children of one cell are marked for coarsening, then it's going to throw away the children and go back to the original cell. I do this whole process 5 times. Okay, so if I look back at the mesh, so I started with a mesh that had 10 cells around the perimeter. The first time around, I replaced each one of these cells by 4 because each one of the 10 original cells was at the inner boundary. The next time, only those 2 out of each 4 child cells sit at the inner boundary, and I refine them, and so on and so forth. So I do this 5 times, and then I come out with a mesh that looks like this. So at the end of this process, let me go back here. At the end of this process, I have a triangulation that consists of all of these cells, and I want to output this again into a file. So what I'm going to do again is I'm going to create an output file stream here, and I'm going to output this into a file called grid2.eps. I'm going again to create an object of type grid_out, and the variable is called grid_out with an underscore. So you already see the convention in deal.II that we always name classes with uppercase letters and variables with lowercase letters. And then I'm going to write this triangulation into this file again in EPS format. And what comes out, of course, is exactly this file if you look at it with Ocular. So there are 2 things that I would like to comment on. And the first thing is to talk about what this actually means here, this triangulation active cell iterator. So an iterator, as I said, was essentially a pointer to an object that I can move from one object to the next, to the next, to the next in a collection. It is a cell iterator. That means it is a pointer that points to a collection of cells. It turns out that the triangulation is not just a collection of cells, but it actually is also a collection of vertices, for example, and it is a collection of faces. Faces are the interfaces between 2 cells. So in 2D, for example, the faces are line segments. In 3D, faces between cells are quadrilaterals. So the triangulation also has a type that is not called cell iterator, but it is called face iterator. And then there is a distinction between active and non-active cells. So I told you that the triangulation class in deal.II can do adaptive refinement. That means that you can get meshes like this here, where you start with one big cell and you refine it. And you could think of this way as, well, if I refine such a cell, then I just throw away the original cell and replace it by 4 new ones. But if you do this, then you end up with something that you cannot undo. It's very difficult to later on then to identify if you wanted to coarsen the mesh again. It would be very difficult to find out how to do this because you have to throw away the mother cell. So deal.II, the triangulation class, actually stores all of the cells. So it stores the original cell and its 4 child cells. And what that means is that there are 2 different classes of cells. There are the ones that are the most refined. These are the ones that we want to define our finite element shape functions on. These are the ones that we want to use for, let's say, integration and so on and so forth. So, but then there's also the original cells, the ones that are not used anymore. And we call these inactive, whereas the ones that we do all the work on, these are we call the active cells. So this type active cell iterator that we have here, that is essentially a collection of all of the active cells that you want to do your work on, all of the cells that you want to iterate over. Whereas if you just wrote triangulation cell iterator, that would loop over all of the cells, whether they're active or not. So in the beginning, in the first step, of course, every cell is active. After the first refinement iteration, you have 40 active cells, but you still have 10 inactive cells. So the loop over all of the active cells would iterate over 40, whereas if you had a loop over all cell iterators, you would have a loop over 50. 10 of which are not active. The other thing that I would like to point out is this part here. So when you deal with curved boundaries like we have here, for example, when you refine this original cell that we had here, so there was one quadrilateral here. When you refine this one, then the question is, well, where should the triangulation put this new vertex on this particular edge? And by default, the triangulation doesn't know what kind of geometry you want to approximate. It might be that you want to really approximate a polygon with 10 corners, right? That might be. Or maybe in this case, we really want to approximate an annulus with circular boundaries. So one of the things that you have to do is you have to tell deal.II that when you want to refine the mesh, where to put a new vertex, so that it can actually pull this particular vertex out, so that instead of replacing this top edge here with let's say 2 little straight edges that are on one line, that it actually pulls this one out so that it lies on the circle. And the same, of course, on the inner boundary. So the way we do this is that we create an object here of type hypershell boundary. So we created an object with this function grid generator hypershell, and there is a corresponding object of type hypershell boundary that describes this boundary as 2 concentric circles. Okay, or let's say if this was in 3D, that's why we call it a hypershell. In 2D, it's 2 concentric circles. In 3D, it would be 2 concentric spheres. And so we need to tell this boundary description where is the center. Okay, and then we need to tell the triangulation to please use this boundary description for every boundary that has an indicator 0. So you can think of the individual parts of the boundary as having different indicators. You might, for example, want to say that let's say in your application, in your user program, that this part of the boundary over here should have indicator 0 and should have one particular boundary description attached to it, whereas this part of the boundary down here should have indicator 1 and should have a different kind of boundary description attached to it. For example, you might want this to be polygonal, whereas this one up here should really be a circle. So by default, all boundaries in deal.II have indicator 0. And so when we say here, set boundary 0 boundary description, that means use this particular boundary description here for all boundaries of your domain. And then the triangulation, every time you called execute coarsening and refinement, every time it needs to create a new vertex, what it's going to do is it's going to ask the boundary description, so in this case the hypershell boundary, hey, you know, I need a new point on this edge that I'm supposed to refine. Where should I put it? And the hypershell boundary will say, okay, I know that I want 2 concentric circles. I know where the center is. That's where your new vertex should be. So that's what these 2 lines do. That's what moves these points out there. So this is essentially what step 1 does. And now one of the things that I would like to go through in the next class is that we talk about how do you play with this. So what are tools, how you, or let's say, what are ideas of how you can replace this triangulation with something else? What are ways how you can, you know, for example, refine towards the outer edge or refine all cells and so on and so forth. That will be what we do in lecture 7 then. So with this, we'll stop on step 1.